All right, let's take a look at the question, the really hard question that we gave you on Friday, where we said we have this 500 kilogram object being pulled along by this rope that's attached to a 80 kilogram elevator, basically, with a guy inside that has a mass of 50 kilograms. So let free to go. 4 seconds after it starts moving, the guy throws the ball at 20 meters per second at an angle of 30 degrees. And we're looking for basically how far the ball goes, how far the ball travels. Well, here's what we're going to do first. Okay? The same thing we always do when we have an inclined plane problem. Let's draw a free body diagram with the force of gravity acting down, okay, Fg, and the normal force acting at 90 degrees. Nothing rocket science so far. This is all very, very straightforward stuff so far. In fact, you're going to find that most of it is. It's just a matter of combining everything. There's a couple little tricky things, but I'm going to call that FH, as we always do. Then we're going to draw that in up here, FH. There's not two of them. There's only one FH. It is the combined normal force and gravity. We're just drawing it in a couple places here. The angle that we have here, by the way, is 30 degrees. So let's label that as well. While we're at it, look, we know there's a force of gravity acting down on this one. And the force of gravity acting down on this one, we know right away it's going to be 130 kilograms times 9.81. So that gives us a force here downwards of 1275.3 newtons. Right? That's not hard either, right? Okay, let's over here get the value of FH and FN. We're not sure what to do with this? Do something. Get the value of FH and FN, exactly as we have in a number of the questions that we've done already. Let's say sine 30 degrees is equal to opposite, that's FH, over the hypotenuse, which is 500 times 9.81. That gives us a value of FH, if we do the math there, of 2452.5 newtons. Let's get the normal force while we're at it, since we're not really sure exactly what to do with this question. Cosine 30 degrees is equal to the adjacent side over the hypotenuse, which is, again, 500 times 9.81. That means my normal force, when you do the math, works out to be 4247.8546 newtons. So far, so good? Easy so far, right? Easy so far. All of us could have gotten this. Okay, every single one of us could have gotten this if we didn't look at this question with fear. Okay, if we look at it with confidence and not fear, then we can all easily get this far. All right. Now the next question we have is, does it move? Does this thing move? Okay, because we've got a coefficient of static friction and a coefficient of kinetic friction. Let's see if it moves. Okay. FSF max, the maximum possible force of static friction, is equal to mu static times the normal force. Mu static is 0.20, and that's given to us in the question. The normal force we just found was 849.571 newtons. That gives us a maximum possible force of static friction. Sorry, no, that's not right. Now, the normal force was 4247.8546. That gives us a maximum possible force of static friction of 849.571. Now, do we know if it moves yet? No, but we're close. Okay, if we redraw it out on a flat surface, which is what I like to do whenever I have an inclined plane problem or a pulley problem, here I have both, so it probably makes sense to draw it out straight like this. We've got a force of our hill. The force of our hill was to the left, and its value was 2452.5 newtons. We've got our applied force, which was our force of gravity. Which was 1275.3 newtons. And then we've got friction. Which way does friction act? Static friction. If, by the way, if it doesn't move, which way would static friction act? Up the hill, right? It's going to act, in this diagram here, it's going to act to the right. Its value, the force of static friction, the maximum possible force of static friction, is 849.571 newtons. Does it move?
Yes.
It does. We're going to say since FH, that's the force that pulls it down the hill, is greater than FG plus SFX max. Since the force down the hill is bigger than gravity that pulls it up the hill and the maximum possible force of static friction, it moves. So here we've done a couple pages on the smartboard here, and all we've done is establish that it moves, which basically I told you that it was going to move anyways, right? So even if you didn't even do this part of it to find out that it moves, okay, could have went a little bit further because I told you basically it was going to move. Well, if it moves, then let's get a force of kinetic friction, because we know there's friction there. Let's get our force of kinetic friction. Let's go back to this last page, though, and copy over a couple of things here. Except it doesn't want to do it. Here, let's do this. Just want to copy over the force of the hill and the normal force, because we know we're going to use those forces again. The force of gravity that was acting to the right, we had already found. The force of gravity was 1275.3 newtons. Again, we're not calculating that again. We already know what it is. Let's get the force of kinetic friction. Since it moves, it's got to be kinetic friction. It's equal to mu times the normal force. The coefficient of kinetic friction was 0.10, and the normal force right here, 4247.8546 newtons. We multiply those together, the force of kinetic friction works out to be 424.7854 newtons. Okay. Has what I've done made sense to everybody so far? We weren't sure where to start, so we calculated the force of gravity. That was easy. We calculated the force of the hill. That was pretty straightforward because we've done that a million times. We calculated the normal force. Then we saw if it moved. It did. So then we calculated the force of kinetic friction. Now I've got all my forces acting here. Nothing to do with the ball throwing yet, but we got to analyze the motion of the system before we deal with the ball throwing. Let's redraw it now. We've got our 500 kilogram object here. We've got our 130 here. We've got our force of the hill acting to the left. It's 2452.5 newtons. We've got our applied force acting to the right, or our force of gravity acting to the right. It's 1275.3 newtons. And we've got our force of friction acting to the right. It's 424.7854. It's acting to the right because it's going to move to the left. It's sliding down the hill. Now we do what we always do. Let's say F net is equal to the sum of the forces, FH plus FG plus FF. And F net is equal to the m times the acceleration, m times a, which is 630, times a equals negative 2452.5 newtons plus positive 1275.3 plus 424.7854. A works out to be negative 1.194309 meters per second squared. Fraser, did you get that number? No. Did anybody get that number for acceleration? Does it make sense, Fraser, where we got that from?
Yeah.
Okay, where'd you make your mistake? Okay. Wouldn't it be funny if that's the only mistake you made through the whole thing? Simple little mistake like forgetting to add that friction? Okay, force of gravity. Okay. So there's the acceleration of our system. On my 4-page answer sheet, there's page 1. Well, it gets more fun, though. It gets way more fun. Now, go ahead.
If your acceleration is positive, then that moves everything up.
Well, okay, let's hold on here for a second here. That's a good question. If acceleration was positive, what would that mean? With the way that I have this diagram drawn, the acceleration is negative, right? Because it's accelerating to the left, the way that I have my frame of reference defined. But in a second, you're going to see that I'm going to change it to positive because I'm going to change my frame of reference. I'm not going to want to analyze the system. I'm going to start analyzing the guy and the elevator. Well, it's moving upward, so I'm going to change it to a positive acceleration because I'm analyzing that upward motion. Hey, does that make sense? Does that answer your question? So the question right now is, look, if the elevator is moving upwards for 4 seconds, how far does it go? How far does it move upward for 4 seconds? We need to know that, right? Because if the guy is throwing the ball out at an angle of 30 degrees at 20 meters per second, after 4 seconds has gone by, how high is he? How high did he start from? Or how high did the ball start from, that is? So we need to know the initial height of the ball. And to get the initial height of the ball, we need to know how high the ball is when it's released after 4 seconds. So we'll find the initial height of the ball. We're going to do that by saying d is equal to VIT plus 1/2 AT squared. This is before the ball was thrown, right? VI is 0, because when this whole thing starts, the elevator is at rest. And if the elevator is at rest, then the guy inside the elevator is at rest, and the ball is therefore at rest as well. So VI will be 0 meters per second. Delta D is what we're looking for. 1/2 of neg 9.8, sorry, not neg 9.81, because the elevator isn't accelerating at neg 9.81. It's accelerating upward at 1.194309 for 4 seconds. Gives us 9.55447 meters. So this is not how far the ball goes. The ball hasn't even been thrown yet. The elevator goes up 9.5 meters before the ball was thrown. So my initial height of the ball is 9.5 meters when it's thrown. Now, here's a big thing right here that I bet even if you had have gone through this, if you had have gotten this far, a number of you would have missed. The ball is thrown at 20 meters per second, right? Wrong. It was thrown at 20 meters per second relative to the elevator. If we want to find out how far it moves relative to the ground, we need to know how fast it was moving relative to the ground when it was thrown. It wasn't 20 meters per second because the elevator was moving, right? It was thrown like this from the elevator, but the elevator was already moving upwards. So what we need to do is take the y component of the ball's velocity of the 20 meters per second and add it to however fast the elevator was moving. So let's get the speed of the elevator at 1.194 seconds. For that, I'm going to say VF squared is equal to VI squared plus 2AD. Again, initially the elevator was at rest at the beginning of this problem, so it becomes VF is equal to the square root of 2 times not 1.19 seconds, at 4 seconds, right? The acceleration is 1.194309 times the displacement of 9.55447. Gives me 4.77723 meters per second. So that's how fast the elevator is moving when it gets to that height. All right, we're getting there. We're getting there. There's like 2.5 pages left here, but it's not really that long, actually. A lot of scribbles and stuff like that. Let's draw a picture of this now. This is like saying we're throwing a ball from a height of 4.160368. 9.55447 meters. This is our x component initial. This is our y component initial. And we want to find out how far the ball goes. Let's get the x components and the y components of the initial velocity of the ball. Let's say cosine 30 degrees is equal to x over 20. X ends up being equal to 17.3205 meters per second. The y component, sine 30 degrees, is equal to y over 20. 10 meters per second plus the velocity of the ball isn't 10 meters per second initially in the y component because we have to add to that the initial velocity of the ball due to the motion of the elevator. The elevator was moving upwards at 4.7 meters per second when the ball was thrown. So if it was thrown at 10 meters per second, but it was already moving at 4.77 meters per second, then we have to add those two together to get the initial y component of the ball. 4.77723 gives us 14.77723 meters per second. So here's the x component of the ball's motion. Here's the y component of the ball's motion. Make sense? We're almost done, actually. My solution wasn't 4 pages. I was looking at this real quickly. I've got it done twice here, 2 slightly different ways. So the solution's only 2 pages. That's nothing, eh? 2-page solution. Well, it probably did scare you a little bit, yeah. Now let's solve it as a projectile motion problem. X and y components. X is v is equal to delta d over delta t. Y is v is equal to vit plus 1 half at squared. The x component of the velocity we just found was 17.32. This is what we're looking for. This is what we're trying to find. We don't know what the time is. The y displacement is negative 9.55447 meters per second. Okay, why? Well, because we found that the elevator moved up 9.55 meters per second in a time of 4 seconds. So the ball was thrown from that height. Therefore, if it's thrown from that height, it has to go down that far before it reaches the ground. So delta d for the y component is negative 9.55447. The initial y velocity is 14.77723. Why? Well, because it was thrown at 10 meters per second y component, but the elevator was already moving at 4. So those combined gave the ball an initial velocity y component of 14.7. Multiply that by t plus 1 half of negative 9.81 because once the ball is thrown, it's only gravity that's acting times t squared. Now that's a little bit ugly solving for t. I told you on a test you'd never have to use the quadratic equation to solve for t. But here you kind of do, or graph it or something. There's actually 2 values for time that come out of this. One is negative 0.54718 seconds. The other is 3.55987 seconds. I'm not going to show you how to get those. Laura can show you how to get those. Which one do you think I want to use? Hayden? Yeah, we're going to use this one, right? The 0.547 doesn't mean anything, does it? It actually does mean something. It would be the amount of time the ball would have taken to go back here would be 0.54718 seconds. But in the real world, it doesn't mean anything. Okay, we go backwards in time, 0.547 seconds to go there. The time we want, though, obviously, is the 3.55. So let's plug that in here now. Now let's solve for the displacement, and we get 62 meters. That's it. That's all there is to it. It's not that bad, is it? It was. It was pretty much impossible. Did anybody? Nobody got the answer. Did anybody get? Anybody on the right track for this? Anybody get fairly close to getting a right answer? Not in terms of a number. I don't care whether you got like you got an answer of 62 or you got an answer of 6,020. Anybody get fairly close in terms of method? Yes. Where'd you go wrong? Was it just the just the gravity? You did everything else right, including adding. Including this? Good for you. Good for you. So you missed an easy thing. It was just a silly mistake, which is easy to do, obviously. Oh, okay. Okay. So you have to have gravity. You have to have friction, both of which are the kind of the easy parts of the question. You did that as well, Josh. Good for you. Good. Oh, you guys were so close to getting a nice ice cold sorbet on a -9 day. Now, honestly here, yeah, you didn't get it, so, okay. Does this make sense to people? I'm not asking could you do this on a test, because most of you probably couldn't. That's okay. But it at least makes sense when I was going over it. For lots of you it did. Some of you it didn't. Don't panic if it didn't, because it doesn't mean you're going to fail Physics 20 if that didn't make sense. It's a tough question. I hope it made some sense at least to you, though. All of a sudden, man, now you see these easier questions, these inclined plane problems. It's like, well, how easy is that compared to something like this, right? That's kind of the idea.